I want you to start learning how to figure out things on your own. And do you know what that actually means? What it doesn't mean is taking the last equation you learned and vainly plugging numbers in, hoping to find the answer in the back of the textbook. Then you give up, you text your friend who might have figured it out, and then you plug it into the formula, it works, you get your marks, and within 3 days, you don't remember a darn thing what you did, and certainly never did understand what you were doing. This is your fault, and it's the teacher's fault. It's built into our education system to not give you the time for deep thinking. And the lockdown is giving you scads of this time, hours per day. Unfortunately, in many cases, it takes many days. So I don't want to just take up the blacksmith problem. I want to do a real deep dive into it, which is what I call a toothpaste problem. That's something you do when you just gotta squeeze that toothpaste tube and just think, there's like one molecule left. And after you've squeezed it and you've used the roller pin in the kitchen on it and you've squeezed the tip, then you get to the point with all your might you can squeeze and dip the brushes in the hole and actually squeeze out one more little drop of toothpaste. And it feels so satisfying to do that. Or when you're trying to suck that last bit of juice out of a plastic freezy and you're sliding your hands up it like it's some kind of trombone. And then you suddenly clue it. If I blow air into the freezy, it'll inflate. And I can, one molecule. And it's just a lot of fun to do. And I can turn it into a sick, twisted form of fun with a problem. So once again, what figuring out ain't is going through the textbook and memorizing all the possible variations of the problem. Or having a teacher whose solutions always begin with, there's a trick to this problem. In both cases, you're treating understanding like it's a power potion in a video game. You have it or you don't have it, and there is no way to accomplish your goals without the trick. This is not a path to understanding what you're doing at all. However, when you're really trying to figure it out, it doesn't feel like it. It feels like you're just losing your mind and you're screwing up. You're hammering away at the problem, rethinking, crumpling up a page, throwing your books around the room and kicking the cat in frustration. Well, that is correct. That's what you should be doing. Deep understanding comes in sweat and tears. Always. Always it comes that way. You can defeat the wizard and climb the mountain without the power potion, but it will be harder work. Just like doing the Olympics without steroids. But if you do it without the power potion, you'll look at the mountain one day and go, I can do this, but it'll be work. But I'm gonna plan my way carefully. Whereas the power potion addict starts to panic, wondering where the video game weak spot is, and they completely lose focus going, where's my power potion? Where's my power potion? The payoff for deep thinking is slow at first, but it grows like compound interest over time, and you get better and you get better and you get better. Thinking that the teacher must provide you the answer somewhere, always. I'm waiting for a student one day on a test to go, the top of the test says, name. And they'll go, where's it on my fact sheet? Where's my name? Oh my God, I can't find it. Like, calm down. Start itemizing what you have. Deep thinking, it's sneaky. It starts to show up when you don't realize it. Just like exercise, it's a slow process where you suddenly realize one day, hey, I'm stronger. We're not trying to get you to do the correct answers, but approach the correct habits of mind. Because I can guarantee you in science, most scientists are wrong most of the time. And it's from their wrongness they try again. When you shoot baskets, you miss more than you hit the basket. Because it wouldn't be much of a game if every time you played you got the basket in. You've got to get this through your habits of mind. Have you noticed the sneakiness of this? Without even trying, think of movies. It gets harder to be truly surprised by movies, even when they try to give you a twist ending. As you watch more movies, you begin to predict character behavior and plot twists, and you may get to the point that you can predict the end of the movie within minutes of its opening. Just 5 minutes in, oh yeah, the uncle did it. This is your brain deeply thinking behind the scenes, whether you wanted to do that or not, and it gets harder and harder for you to accept movies without going, I've seen this 100 times before. Now, you can probably predict the exact reaction of your parents these days. Any married person will know that they can fight with their husband or wife without even being there going, I know what I'm going to say. I know what she's going to say. You've become very good at building up predictions in your head without actually planning it. So at grade 6, you're 6 years old, you ask your parents, why can't I have a crocodile? Or can I have a crocodile? And you're completely mystified by your parents' negative reaction. Now you know, I'm not even going to bother asking if I can have a meerkat. Even though not once in your life did you ask your parents for a meerkat. You asked them for a crocodile. But you got a greater message behind the scenes about this. Now we go back to our blacksmith heat capacity problem. Cast iron has a heat capacity of 0.49 kilojoules per kilogram per degree C, while water is 4.184. So taking a quick look at these two numbers, they have the same units. The water one didn't do something sneaky like put joules per gram. They're the same units. So if you look at those two numbers, they're nearly a factor of 10 apart. Water will soak up almost 10 times more heat. So cast iron and water would be the difference between a block of wood and a sponge. Sticking them in a tank of water. The sponge will soak up water. The block of wood will not. So cast iron doesn't soak up much heat, which seems really weird that the water can hold heat 10 times more effectively than metal. Now, this is why water is such an effective quenching agent. So if our blacksmith takes an 800 degrees centigrade 1 kilogram horseshoe and plunges it into 1 kilogram of water at 20 degrees Celsius, what final temperature will the water bath reach? Well, the most likely thing you're going to try to do first is just start plugging it in to the equations. But what you have to do is see it for what it is. It's a conservation of energy problem, acting on two different substances. The energy starts in the horseshoe and can be written as Q equals MC delta T. But we're going to be dealing with water as well, so we better subscript these. So I put I for iron. Now the energy will be transferred to the water, and I've colored that equation in blue, but our proper subscript notation, we would write it like this. And the key here is to realize that there is nearly zero chance of the delta T being the same. This would have to be the same substance and the same mass for this to happen. And the masses, I have made them numerically the same in this problem. They're both 1 kilograms, but they are not the same algebraically, meaning we are talking about two different substances. If by sheer coincidence they're both 1 kilogram, they are still different substances. And so if you wanted to use this equation algebraically, you cannot drop the subscripts on mass or the heat capacity because they are definitely different materials. There is an approximate method of solving this. We can pretend the water starts at 20 degrees C and the cast iron will cool to this temperature starting from 800. We take the two numbers, M1C1 delta T for iron, and I'm going to expand it to the TF minus TI so we can see, and we plug our numbers in. The TF minus TI is going to be a negative number, and we get almost minus 400 joules. And of course it's a negative number because it had to give away heat. So the loss of heat is a negative. Now where did this 382 joules go? Well, the 382 joules would have moved into the water. So now the water is going to go to some final temperature starting at an initial temperature. We know the initial temperature of the water exactly like we knew the initial temperature of the iron. We don't know water's final temperature, but we know water will have 382 joules of energy transferred to it. So we can plug everything into the formula and solve for TF. And I rearrange a little bit. I expand the brackets. I've dropped all the units along the way because I just don't want the gobbledygook in your way. And when we're done, I get a final temperature of 111 degrees C. Warning, warning, does not compute. Now we leave math class and move back into physics world. This is not a possible answer. First off, it's climbed to 111 degrees, which is 11 degrees over the boiling point, which means this equation doesn't work there. This equation can only work inside one phase of a substance. That is, MC delta T can only work where there's no state change. So it can work from just above 0 to just under 100. It can work after 100 when water's vapor. It can work below 0 when water's solid. But you can't use this equation when you cross a freezing or boiling point. And that's something that wouldn't happen in math class. A teacher wouldn't say, oh, don't try to compute y equals x squares for 70. Crazy things happen there. It doesn't work that way, but in physics it does. The second problem is, wait a minute. We said the iron was going to cool to 20, but we found that the water would climb to 111. So that means as the iron's cooling, the water actually heats up more than the iron. The iron couldn't possibly have cooled all the way to 20 because the water you're trying to cool it with is warming up past 20. So two problems have developed. But you'll see we're actually pretty close to what's going to happen. Again, math teachers would say use the equation, period. But in physics and in chemistry and places like that that tie to the real world may say, you only got part of the problem, buddy. You know, you figured me out for a range, but you can't cover melting point. And you certainly can't cover warming wood until it bursts into flames. That would also cease to be MC delta T. Now let's go back to our habits of mind pertinent to this question and think through what we did wrong. You don't start calculating values until you know exactly what you are after. We must ask ourselves what is known and unknown about this problem and how to calculate the temperature change when the iron cools to an unknown temperature because the water itself is changing temperature as the iron cools. The key to this problem is which of these variables, the heat, the mass, the heat capacity, the change in temperature, or one of the individual temperatures, TF, TI. That's the key thing to think about. You can pause this slide now to actually dwell on this. What is the value that is going to be driving the equality of the two equations? And this pause to think it through, especially on the stress of a test, it's like you're giving a speech and you just choked up in front of the class, or you're like, do you take her to be your lawfully wedded wife? And the guy starts going, and the girl's like, is he having second thoughts? And the guy's like, oh no, she's going to think, and then you realize later that little stammer where you paused for thought and you watch a video of it, you realize it was like an eighth of a second. You were the only person thinking it was an eternity. This is an appropriate lag to starting a problem. No soldier is going to run across the battlefield before spending a good long time examining the field first for all its traps. And this is something we're not pushing enough in school, or we push and your desperation to find a solution makes you panic and go diving into the equations before you've figured out what it is you're really after. One way around this, doodle. Create yourself an illustration as you go. So we're dealing with temperature. So I'm going to make a thermometer and list the things that I know and don't know on it. I know iron starts 800 degrees centigrade and it's going to cool down. And water starts at 20 degrees and it's going to warm up. Well, iron will reach a final temperature that we will call TF. And we obviously don't know it because that's part of the problem. Water is going to warm up, and wait a minute. Once the two have been left in contact together, they're going to be at the same temperature. So I slid the two arrows off of each other a bit so you can see. But in the end, they will share the same final temperature. And that's our key to this problem. Temperature difference is not shared. The delta T for iron does not have to be the same as the delta T for water. In fact, it isn't even possible that they would be the same unless they had identical heat capacities and identical masses in the problem. The delta T for water will not be the same drop for iron. However, they're going to land on the same final temperature. And that's the key. Not delta T, the absolute final temperature will drive this problem. Now what we have to do is express this in mathematical terms. And again, to repeat myself, the math of physics is not hard compared to the same level in your math class. It is almost 2 years behind, in fact. It is getting the idea of the reality first. Once you understand what to do, then how you do it drops to grade 10 math. Therefore, in this problem, if we expand our two equations, we see what they're really going to share is the TF. Only the energy exchange and the final temperatures will be shared. Once you spot this, you are back to grade 10 math. If it takes you half an hour to realize this, then it is your time well spent. And this finding the key to the problem, that's the big difference between math and physics. Now let's go pure mathematical. Here is the expansion of the two formulas. The only difference in the upper one and the lower one is I'm putting in the subscripts so you understand we're dealing with iron. Now, since the final temperatures are the same, I'm just going to put TF in both equations, but I'll keep the subscripts on everything else because those are not shared between the two problems. The fact that I created identical masses on the first example means you lucked out and the mass is the value of 1. But the mass of iron and mass of water are entirely separate concepts. Now let's think about our problems a bit more here. We'll isolate them here. I've deliberately put a negative on the Q value for iron because we know it's going to be a negative number. Right? It's giving up. So that's where we sort of have to make a decision and put it in there. It's similar to free body diagrams where you had to make up your mind which way should be negative. So the heat lost is a negative. The two Q's must be the same because the heat going from the iron to the water has to equal. So I can expand the two formulas and equate them to each other. Now at this point, I'm just going to do it numerically. I've dropped the number 1. It doesn't count. I've written 0.49 and the temperatures. I've dropped all my units to keep this nice and clean looking for the time being till you get the hang of this. And I'm going to pull off a severe rounding because it just doesn't matter. I just want to be able to do this nice and clean and get nice clean numbers. And you can see here, once we were at this point, it's just grade 10 rearrangement. It'll collapse to this. We still get beyond 100. So our calculated temperature dropped from 111 to 106. That was the difference from not spotting that the water was warming up, and so the final temperature of iron could not possibly be 20 degrees. And when we accounted for that mistake, it only made a 5-degree difference on the final temperature. But this is the correct way to do it. But what's wrong with it is we've exceeded 100 degrees, so the water is vaporizing. So it's no longer a simple problem. Could we still figure it out? Maybe. Let's start squeezing this toothpaste. Since the maximum temperature water can reach is 100 degrees, and after that it cannot reach a higher temperature until it is all turned to steam, this implies that we now know the final temperature of both substances must be 100. So using our brains, we can now force this event to be so. Because we calculated it's shot past 100, so we have to pull back and start here equating the two formulas again, but now we are going to insist the final temperature is 100. You can carry out this math yourself. Watching it will always look more complicated than doing it. Comes together. Looking good. Rearrange a bit more, or just repeat the rearrangement because I made a mistake. And it comes out to, what? Minus 351 joules equals 334.7. What TF? How on earth can minus 351 equal 334? What is going on here? Why didn't the two equal the same? Well, it's because we deliberately forced one of those numbers to become 100. The negative value is fine. Iron lost 351 joules and water gained around 335. The loss on the negative and the gain on the positive, the negative is fine. The problem is that 17 joules have gone missing. Right? Iron lost 351 and only about 335 appeared in the water. So where did the 17 missing joules go? Well, this is, again, it's a physics problem. That must have gone to boiling the water to steam, which would mean we would need to use the Q equals MLV formula for vaporizing water. And given that the vaporization of water, the boiling point where water is turning to steam, takes 2,256 kilojoules per kilogram, which is the same as 2,256 joules per gram, right? What is the mass? We rearrange and we find about 7 milliliters of water, or about a teaspoon of water boiled away. That's where the 17 spare joules went. Liquid water absorbs heat at 4.2 kilojoules per kilogram for every degree, but at the boiling point it will absorb 2,200 kilojoules per kilogram. So warming water 1 degree, you will need 4.2 kilojoules. Taking the same amount of water at the boiling point and vaporizing it, you need over 2,000 of them. Turning water to steam sucks up energy like you wouldn't believe. So this is how math and physics depart. You got to start going, where did the energy go? And do you think the scientists that invented Q equals MC delta T spotted that? Many times they spent years trying to figure out where's the missing energy gone? Biologists were driven crazy trying to figure out in the cells, where did the energy go? You start tracking it down, and this is how discovery happens. By making mistakes and getting minus 351 equals 334. And I'm like, I'm positive on my math. What the heck is going on here? Wait a minute. Some of the water was evaporating. And that's how they discover the next formula. Not by checking the answer in the back of the textbook. But guess what? We're still wrong. It still won't be the correct answer if you carried this out. And this is where it gets really cool, and I would like you all to research just a little bit. The moment the iron hits the water will be heated so intensely it will flash into steam. So long before the liquid water is touched, there is an immediate creation of steam, which is governed by the heat of vaporization formula, not the warming formula. This forms a jacket of steam around the metal and keeps it from touching the water. So for a really long time, like a couple of seconds, there is near instantaneous creation of steam sucking tons of heat away. Without this knowledge of the true mechanism, all the math in the world will not give you the correct answer. So it's not going to be warming first, then turning to steam, like when you put a kettle on. This is going to be instant creation of steam. And it won't penetrate far. Some of you may have accidentally one day touched a hot stove, but your hands were wet, and you heard that psh of steam, and you actually got away without burning yourself. Because the iron, if you look at this picture, is actually not touching the water at this point. It's now got a steam barrier between it and the water, and that protects it. So if you were a fish and that blade passed through the water a centimeter away from you, you might not feel any heat. But if the blade came in the water and stayed put for several seconds, then once the steel cooled down enough that the water actually touched it, then you would start feeling the heat pouring into the water. No math formula manipulation will teach you this. This is the reality you must investigate. Now, I want you to watch this video here. I won't show videos in a video. Watch the slideshow, go to the video. Your hand, when people plunge their hand into liquid nitrogen, is the same as the piece of iron. So your hand is the iron going into the liquid, which is liquid nitrogen. And the nitrogen boils so rapidly that your hand is shielded by nitrogen gas. If you held your hand in the liquid nitrogen for several seconds and your hand cooled down enough for the nitrogen not to flash into steam but touch you as a liquid, say goodbye to your hand. This effect of a gas barrier insulating between a solid and a liquid flashing to steam is called Leidenfrost. So let's look at it. Not the video. Leidenfrost is, this is the Bifrost. When a person stuck their hand into liquid nitrogen, you can see the shielding layer of gas forming on them. Thousands of little bubbles, so they have literally not touched the gas. Now here's the weird part. If there was a deep lake full of liquid nitrogen and you jumped into it, you would fall through that liquid nitrogen almost like you fell through air, because you would actually create an air pocket around you and you would plunge through the layer until you cooled enough for the liquid nitrogen to touch you. So you would find it impossible. If I threw you in a body of liquid nitrogen, you would be incapable of staying afloat, because as you paddled, you'd just be paddling gas for like a couple of seconds till it suddenly touched you and you froze to death. Here are some close-ups of water droplets engaging in Leidenfrost. The droplet hits the hot surface and it forms an air hockey puck. And scientists have studied this effect extensively. Here is a website link that really gets into the physics of it. You can watch this guy doing Leidenfrost at home. Here's another example. You can do this at home by heating up a skillet, tossing a bead of water on it, and you'll watch the bead of water go and skip all over the skillet without touching it. So there's a lot of rich research on Leidenfrost that you could do. Here's another example of the tradition of Leidenfrost being used in the kitchen. It was the classic test that your skillet is hot enough for eggs or pancakes, is you throw some water droplets on the skillet and they just start skipping around the surface like air hockey pucks, and you're at the correct temperature. This effect, dimly related to it, comes into re-entry physics. When an object is re-entering the Earth's atmosphere, the flame around the capsule, it's much, much more complicated than this, but basically, as the capsule's heat shield evaporates, there's a partial barrier to the heat of the atmosphere around it, and as long as the heat shield is burning away, you're shielded. Later heat shields didn't do this. The space shuttle heat shield simply was square one an insulator. It was simply trying to block the flow of heat. It wasn't evaporating itself as it went. These early heat shields evaporated, or what they call ablate. They boil off into space and create a layer of gas between you and the deadly heat. The space shuttle tiles were not only insulating, but their heat capacity is near zero. This tile has been heated till it's glowing red hot. It's many thousands of degrees, but it contains so little heat that you can pick it up. If you want to understand the difference, if you turn your oven on to 400 degrees and you heat popcorn in the oven and you heat a big chunk of beef or pizza, if you reach into that 400 degree oven, you can easily grab out a handful of popcorn and start eating right away. The loaf of bread is going to be a little bit nasty. You reach into the oven at 400 degrees and plunge your hand into water, grease, or touch the walls of the oven, you will be burned horribly. The temperature was the same on everything in the oven, but the heat capacity wasn't. And the metal is so conductive that not only does it hold a lot of heat, but it dumps it into your hand really fast. So the space shuttle tile holds little heat at all, and it also doesn't conduct it worth a damn. So you can hang on to this red hot tile for a little bit. If you take a look at a video of them doing it, they're constantly manipulating their fingers. You'll feel the heat, but the important thing is not to grab it by the flat face. Then you'll actually go a little bit ouch on it. But if that was a chunk of metal, he would have lost his arm already. Now, how could you turn some research into a Leidenfrost or a heat topic onto a project? This is my example of putting all the formulas together. I've always been looking for a really neat graphic to do this, but this is all we've done so far in the entire course. I know it's a lot of work that you guys have done under very difficult circumstances, but this is it. We did those basic kinematic equations in black. From there, we did forces, MA. And from forces, we did MAD, which is work. We did kinetic energy. And from that, we did heat. Well, Q is energy. Energy is the same as work. We get energies in work from forces over a distance. Forces are composed of accelerations. Well, distance, velocities, and accelerations in those equations in blue all would involve the black equations from kinematics. And if we move into heat, we just switch it to the letter Q. So if you could give me some sort of intelligent tour of these formulas, then you're good to go. And to really knock it out of the park is to pick a new formula you've never learned before and explain to me how you learned it. And again, with my input. So this is taking up the one problem on the blacksmith, and I've taken it and built it into a big toothpaste presentation of like, how much could I squeeze out of it? And so what I've got here would be the lead-in to a completely acceptable project, except I only did one math demonstration in it.